Hello and welcome to today's class. Today we'll be looking at thin cylinders and we'll be looking at the stresses which are set up in a thin cylinder due to the pressure inside that cylinder. We'll be talking about those stresses that are set up. There's three mutually perpendicular stresses: hoop stresses, longitudinal stresses and radial stresses. We'll have a look at those with regard to thin cylinders and work out how we can calculate what those stresses are in terms of the pressure and the geometry of the cylinder. We'll then go on and have a look at any changes in length that are caused by those pressures. In some industries where you get a pressurized cylinder, you might well be selling a product by volume, let's say the petrochemical industry. So it's important to understand what changes in lengths, diameters, and so on you get when you fill those containers with fluids. And therefore we can work out what change in volumes we would get. So we'll have a look at changes in lengths, and then from that we can work out what changes in volumes we will get. Okay, so let's consider a thin cylinder. I'll draw that thin cylinder, or half of that thin cylinder. It's a free body diagram. We're going to pressurize it, and that is going to set up some forces on or some stresses on that cylinder. And we're going to work out what those stresses are. So there's my cylinder. Something like this. We would have a pressure on the inside of that cylinder, so we've got a pressure internally. Clearly that's going to act normal to all of these inside faces. So we've got an internal pressure, P. That's going to set up some stresses. So on these bottom faces, you would have stress. And we're going to give that a subscript H for hoop stress. It's acting in the hoop direction. Because if we consider a small section of material sat on that surface, actually there are three mutually perpendicular stresses. Okay, we have our hoop stresses, which are running around the outside of the cylinder. Hoop stresses. Those are caused ultimately by the pressure inside trying to expand this cylinder. We also have some longitudinal stresses, acting at 90 degrees to those. My longitudinal stresses. Those are caused by the pressure acting on the end plates of the cylinder, trying to expand the length of that cylinder. We'll calculate what those are. And there's also a stress acting out of the plane called the radial stress. Now, with thin cylinder theory, as long as our ratio of diameter, the thickness, is about 1 in 20 or greater, we can neglect that radial stress. That radial stress we will assume is constant through this thickness, and it's also insignificant in comparison to these hoop stresses and these longitudinal stresses. So we're just going to consider these two stresses, the hoop stresses and the longitudinal stresses, which are acting at 90 degrees to each other. Hopefully that looks familiar to you, that sort of thing. We've talked about that when we've been talking about complex stress. And I've been saying this is sigma x and this is sigma y, or vice versa. Again, we'll be able to work out the stress and range plane of interest and also the principal stresses. Okay, we've got much the same scenario here. We've got a piece of material, we've got two mutually perpendicular stresses, the hoop stress and the radial stress. So let's put some dimensions on this. So let's say this is of length L and of thickness T. Okay, and given those dimensions and this pressure, we can work out what the hoop stress is, which is acting internally within the material, acting in this direction. We can also work out what the longitudinal stresses are. Okay, so let's work out what those hoop stresses are. So the first thing that we're going to do, we're going to look at this structure from underneath. So let's draw my eye here. I'm going to look in that direction. Okay, so what would we see? Well, we would see something like this. Okay, got my cylinder. Looking from underneath. These are the walls that I've chopped through. Okay, and my hoop stress is going to be acting on this surface. And this surface. My pressure is going to be acting on this surface here. Okay, perpendicular to that surface. Okay, and we've drawn some dimensions now. We've started that is of length L, thickness T, and this is we didn't mark this on the last diagram. If we draw that to the middle there, if we're assuming these are quite thin, we call that D, our diameter. Okay, so the forces acting into the page are going to be the pressure, force caused by the pressure on this surface here. Okay, so the force into the page, like that. Force into the page is going to be, you know, pressure equals force over area. So therefore, my force is simply my pressure times by my area. Internally, we've said we've got a pressure acting on this surface, P, and my area is D times by L. Okay, F equals PdL, that's the force into the page. Now, the force coming out of the page resisting that, so we consider we're looking in this direction. So my force acting upwards, we've just worked out PdL. My force acting downwards is going to be the force caused by these stresses on this surface, on these surfaces that we've cut through. That's resisting that cylinder from expanding. We're trying to stop that from bursting. Okay, so the force out of the page Well, saying no, you know, pressure is force over area. We also know stress is force over area. Okay, so therefore the force out of the page is simply going to be stress times by area. Now, the stress we're saying on these red surfaces, we're calling sigma h, the hoop stresses. Okay, so looking back at our diagram, it's our hoop stresses which are acting on those surfaces that we've cut through. Okay, so my stress, sigma h, and my area, well, it's T times by L, and there's two of those, so it's 2TL. Okay, so if we know this is set in equilibrium, the forces into the page are equal to the forces out of the page, we're simply going to equate that to that. So we're simply going to say P, therefore PdL equals sigma h 2TL. Okay, now clearly that length cancels with that length, so we can rearrange that to get my hoop stress. My hoop stress equals PD over 2T. Okay, so the stress internally within that structure, the hoop stress is PD over 2T. The pressure times by the diameter of the cylinder divided by 2 lots of the thickness. My hoop stress equals PD over 2T. So my hoop stress equals PD over 2T. So those are my hoop stresses. Let's now calculate what my longitudinal stresses are. And in order to calculate what those are, so we're going to have to consider the pressure internally acting on the end plates. So now let's, instead of looking from underneath on this structure here, let's chop this structure in half with the end plates on it, and let's consider what we would see. Okay, so my cylinder is going to look something like this. My cylinder, I've now drawn the end plate on it. It has a thickness, T. We've got a pressure on the inside of that cylinder. And we've already considered the fact that this pressure is acting on these outside faces, which is resulting in that hoop stress. We're now also going to consider the fact that this pressure is acting on these end plates, which results in our longitudinal stress. Okay, so we've got a pressure acting on those end plates as well. Now, remember, this has a thickness T. D. So if we were to take that structure now, and we're going to chop it in half, and we're going to look in that direction. So this time, I'm going to draw my eye here. And we're looking in that direction. Okay, and what would we see? We'd see something like this. We'd see cylinder. Thickness T. Now pressure this time is going to be acting on this circular surface, and our our longitudinal stresses, thing which is trying to stop our cylinder from expanding in length, are going to be acting on these surfaces here. Okay, so my longitudinal stress is going to be acting in that direction. Okay, it's acting on this blue shaded region here. Okay, that's my longitudinal stress acting on that surface, and my pressure is acting on this surface. This is diameter D and thickness D. Okay, so we're going to do the same thing. We're going to consider the forces acting into the page being equal to the forces acting out of the page. Okay, so let's do that. So the forces acting into the page. So forces into page. So pressure equals force over area. Therefore, my force is simply my pressure times by my area. My pressure we've called P. My area is the area of this circle, which is pi r squared. Pi r squared, or in terms of my diameter, it's going to be P times by pi d over 2 squared, which is equal to p pi d squared over 4. So that's the forces into the page. Now the forces out of the page caused by this stress. You know, stress is force over area. So therefore my force is simply my stress times by my area, which is, we could work out that outside circle and subtract that inside circle to get my area. But given the fact that this is a small thickness, that is very close to the circumference times by the thickness. That's approximately this area. Okay, so we're simply going to say my longitudinal stress times by the circumference times by the thickness. Now the circumference of a circle is pi d, 2 pi r. So pi d by the thickness t. That's going to be the forces acting into the out of the page. Okay, so we've got forces acting into the page caused by this pressure, and the forces acting out of the page caused by this stress. Now again, we're going to say they're in equilibrium. This thing is not moving anywhere, and those end plates are trying to resist that pressure, stopping the cylinder from getting longer. So therefore, we're simply going to equate this to this. Okay, so we're going to say p pi d squared over 4. So that's p pi d squared over 4 is equal to sigma L pi dt. Sigma L pi dt. Okay, now clearly pi cancels with pi. That t, that d. Let's redo that again. P pi d squared over 4 equals sigma L pi dt. So pi cancels with pi. That d cancels with the second d there. So what do we end up with? We end up with p over 4 d over 4 equals sigma L times by t. So therefore sigma L equals p d over 4 t. Okay, that's my longitudinal stress. So if we look back at our previous slide, we had this. So my hoop stress was PD over 2T. We've now just said that my longitudinal stress equals PD over 4T. Okay. So hoop stress, PD over 2T. So that's the stresses in this direction. Longitudinal stress, PD over 4T. That's the stresses in this direction. Okay, so we've now worked out that the pressures inside the cylinder are causing hoop strains and longitudinal strains, and we can calculate what those strains are based on the pressures and the geometry of the cylinder. Let's now consider how that cylinder changes in length due to those strains, or due to those stresses. Okay, so let's consider this small piece of material. We're going to have hoop stresses in one direction, and we're going to have longitudinal stresses in the other direction. Okay, so let's draw that. Okay, so there's my small piece of material. And we've got hoop stresses in one direction. Let's draw those vertically. It's my hoop stresses. And we've got longitudinal stresses Okay, so let's now consider the following strains. Okay, now we know Young's modulus, stress over strain. Young's modulus equals stress over strain. So therefore, strain is simply the Young's modulus, the stress divided by the Young's modulus. So let's consider the longitudinal direction. Okay, so strains in the longitudinal direction. So there are strains caused by the longitudinal stresses, and those are simply the longitudinal stress divided by the Young's modulus. Okay, so longitudinal strain caused by the longitudinal stress is going to be the longitudinal stress divided by the Young's modulus. But in addition to that, there is another strain in this direction, which is caused by the fact that we're stressing in this direction. Okay, so if we're causing a stress in this direction, the structure is going to get thinner in this direction. Okay, so if I were to draw that, my deformed shape due to those hoop stresses is going to look something like this. Okay, so the hoop stresses are clearly causing a longitudinal strain. Okay, and that's related via our Poisson's ratio. Okay, so we know Poisson's ratio is simply negative lateral strain over the longitudinal strain. So in the longitudinal direction, not only do we have the strain caused by the longitudinal stress, we also have an additional strain in that direction caused by the hoop stress, and that is negative because it's getting smaller. It's trying to contract in that direction. The lateral strain divided by the longitudinal strain. So that's caused by Poisson's ratio times by the hoop strain, the hoop stress divided by Young's modulus. Okay, so clearly that is the strain caused by the hoop stress in this direction. How much strain we get in the longitudinal direction is simply going to be the lateral strain. It's going to be Young's modulus times by the longitudinal strain, a longitudinal strain. Okay, so we've got two components. We've got the longitudinal strain caused by the longitudinal stress, and we also have the longitudinal strain caused by the hoop stress. Okay, so the total strain, we're going to add those two bits together. We're going to add this strain and this strain. So the total strain in the longitudinal direction, longitudinal strain, is simply going to be the strain caused by the longitudinal stress minus Poisson's ratio times by the strain caused by the hoop stress. Okay, so my total strain in that direction is going to be that. Clearly, we can factorize that. So my longitudinal strain equals 1 over my Young's modulus times by my longitudinal stress minus Poisson's ratio times by my hoop stress. Okay, so that's the total longitudinal strain. Now, in the same way, we can show our hoop strain is made up of two components. It's clearly the component caused by the hoop stress minus Poisson's ratio times by the component caused by longitudinal stress. Okay, so we have those two components. Now, if we look back to what we had before, our hoop stresses, PD over 2T, our longitudinal stresses, PD over 40, clearly we can insert those into there. So we could say for our longitudinal strain equals 1 over the Young's modulus times by longitudinal stress minus Poisson's ratio times by the hoop stress is simply going to be 1 over E longitudinal stress PD over 40 minus Poisson's ratio in the hoop stress PD over 2T. So that's my total longitudinal strain. And in the same way, we could say for my hoop strain, so my hoop strain equals 1 over E of my hoop stress minus Poisson's ratio times by my longitudinal stress, which is simply going to be 1 over E times by the hoop stress, which is PD over 2T minus Poisson's ratio, longitudinal stress, PD over 40. Okay, that's going to be the hoop strain. Okay. So if we look back to our previous diagram, we've just calculated that the longitudinal strain is equal to 1 over the Young's modulus times by PD over 40 minus Poisson's ratio times by PD over 2T. Okay, now that we've got the strain, we can work out the change in length. Okay, so let's consider what is the definition of strain. So if we consider longitudinal strain, equals change in length over original length. So therefore, change in length is simply strain in the longitudinal direction times by the original length. The strain in the original direction, in the longitudinal direction was 1 over E PD over 40 minus Poisson's ratio PD over 2T times by the original length. Clearly we can factorize that. So we've got PD over 4TE lots of 1 minus 2 lots Poisson's ratio by the length. So that's the change in length due to the fact that we're pressurizing the cylinder. Okay, so we've got the change in length of our cylinder. Now, how did we get that? We got that by considering the longitudinal strain. Okay, the longitudinal strain equals change in length over original length. In order to calculate the volume, due to the fact that this cylinder is pre-pressurized, not only do we need the longitudinal strain or the change in length of the cylinder, we also need to understand the change in diameter. And once we've got those two dimensions, we can think about calculating the change in volume of the cylinder. So longitudinal strain, change in length over original length. Let's now introduce you to diametral strain. So diametral strain would simply be the change in diameter over the original diameter. So longitudinal strain, change length over original length. Diametral strain, change in diameter over original diameter. We can also think of circumferential strain. So circumferential strain would be the change in circumference over the original circumference. Okay, so when we're talking about strain, we need to consider the direction that we're considering the strain in. Is it in the longitudinal direction, changing length over original length? Is it in the diameter direction, changing diameter over original diameter? Or is it in the circumferential direction, changing circumference over original circumference? Okay, so longitudinal strain, diametral strain, circumferential strain. Okay, so let's think about those definitions. A longitudinal strain equals change in length over original length. Diametral strain is equal to the change in diameter over the original diameter. And the circumferential strain equal to the change in circumference over the original circumference. Now, looking at our original diagram, the circumferential direction is actually the hoop direction. Okay, so the circumferential strain is actually the hoop strain. Okay, so circumferential strain will actually give that this symbol. Our hoops is the same as our hoop strain, is equal to the change in circumference over the original circumference. So let's consider that. Let's consider what our circumferential strain is. If we times through by circumference, we're going to end up calculating what our change in circumference is. So our change in circumference equals our hoop strain times by our original circumference. Our hoop strain. Now the original circumference of a circle is pi d. Okay, so that's the change in circumference. So the new circumference will be the old circumference. It's the change in circumference. Now the old circumference was pi d. The new circumference, the change in circumference is simply the strain times by pi d. Clearly we can factorize that. We can take pi d out. We've got 1 plus, this is the hoop strain, and plus the hoop strain is going to be the new circumference. So the old circumference was pi d. The new circumference is pi times by that lot. So the original cylinder had a diameter d, pi times by that distance. The new cylinder, the diameter is no longer just d, it's d plus this. Okay, this is the new length, the new diameter of our cylinder. Okay, so pi times by this distance is the new circumference. The old circumference is pi times by this distance. So if we look at the old diameter, that is d. New diameter is this, d lots of 1 plus the hoop strain. Okay, which clearly is d plus d times by the hoop strain. Okay, so we can see the old diameter was just d, the new diameter is d plus this bit. So this is the change in diameter. Okay, so we now know what the change in diameter is. It's this. Okay, so we can work out what our diametral strain is. Our diametral strain equals the change in diameter over the original diameter. Now, the change in diameter we've just said is this, is D times by the hoop strain. And the original diameter was D. Okay, now clearly that and that cancel out. Now, what does that leave us with? What we've just said is that our diametral strain is equal to our hoop strain. Okay, so our diametral strain is equal to our hoop strain. Now, that's quite a significant observation, and we'll use that moving forward. So when we want to calculate the change in volume of the cylinder, we know the diametral strain is the same as the hoop strain. Okay, so we've now calculated the diametral strain is the same as the hoop strain. So we're trying to calculate the change in volume of this cylinder. We've worked out the change in length. We can now work out the change in diameter due to the fact that we know the diametral strain is the same as the hoop strain. If we know the change in diameter and the change in length, we can work out the change in volume of the cylinder. Okay, so let's do that. So we're going to consider our change in diameter. Change in diameter is equal to our original diameter times by the diametral strain, which is diametral strain. We've just said that our diametral strain is the same as our hoop strain. So that's diameter times by the hoop strain. It's the same thing. Okay, now we saw earlier when we were considering the longitudinal strain, we said this, it was made up of two components, the stress caused by the longitudinal stress, or sorry, the strain caused by the longitudinal stress, and the strain caused by the hoop stress. We also know, we also showed this, that our hoop stress was made up of two components. We've got PD over 2T minus Poisson's ratio PD over 4T. Okay, so the hoop stress was made up of two components. The stress caused by the hoop in the hoop direction, the hoop stress. So that's the stress, that's the strain. So the hoop strain is made up by the strain caused by the hoop stress, and it's also made up by the strain caused by the longitudinal stress. So we know the we know the hoop strain. Okay, so we can now insert that. Okay, so the change in diameter is the original diameter times by the hoop strain, which is 1 over E, lots of PD over 2T minus Poisson's ratio PD over 4C. Clearly we can factorize that. We've got PD squared over 4TE, lots of 2 minus Poisson's ratio. Okay, so that's going to be our change in diameter. Okay, so now that we've got that, we can calculate the change in volume. We've got change in length, we calculated that already. We've now got change in diameter, so therefore we can calculate change in volume. Okay, so the change in diameter is given by that, and we saw earlier the change in length is equal to PD over 4TE, lots of 1 minus 2 lots of Poisson's ratio times by the original length. So change in diameter, change in length. We know that for our cylinder since we pressurized it. So what we can do now is calculate the change in volume. Now, in order to do that, we're going to simply add 3 mutually perpendicular strains. Okay, now that statement is true. However, it's easier to prove using Cartesian coordinates rather than polar coordinates. So let's consider something in Cartesian coordinates, which is being pressurized, and let's work out the change in volume of that. But rather than talking about diameters and radiuses and theta and so on, we're going to be talking simply about X, Y, and Z. So let's consider a piece of material. We've got a piece of material. I'll draw it like this. There's my piece of material. We're going to pressurize that such that its new shape looks something like this. Okay, so it's got smaller in that dimension. It's got smaller in this dimension. And it's also got smaller in this dimension. Okay, so the new shape looks something like that. So there's the original volume. Let's put some dimensions on that. Let's say the original, let's say X is in this direction. Original X length is that distance there, and it's got smaller by a distance, delta X. Let's say Y is in the vertical direction. So originally it was of length Y. And due to the fact that we've pressurized it, it's got smaller by this dimension here, which is called delta Y. And Z, if we say Z is into and out of the page, originally this thing was Z meters in that direction. And it's got smaller. So the original shape would be back here. It's got smaller by a distance, delta Z. So the volumetric strain is the change in volume over the original volume. We need to calculate that because we're interested in the change in volume. Okay, so volumetric strain equals change in volume over original volume. Change in volume we're interested in the original volume was clearly X, Y, Z. Okay, this distance times by this distance times by this distance. So we're interested in change in volume. So let's calculate that. Okay, so the change in volume of this shape is equal to the strip at the back. That's the back plus the strip at the side plus strip on top. Now, what do I mean by that? The strip at the back. Well, clearly that is going to be, try and draw that one here. So we've got the strip at the back, going to be this bit here, isn't it? This red section here. caused by the fact that it has got smaller by this distance, delta z. Okay, so that's the strip at the back. Plus the strip at the side. What's the strip at the side? Well, it's this bit here, isn't it? Okay, I'll shade that in green. Strip at the side, plus the strip on top. This bit here. There. I'll shade that in black. Strip on top. Okay, now what's the volume of the strip at the back? Well, it's x times by y times by delta z. Okay, the strip at the back is equal to x, y, delta z, plus strip at the side. What's the volume of the strip at the side? Well, it is delta x times by delta y times by z minus delta z. That's this length here, isn't it? Okay, so it's x times by y, delta x times by y times by z minus delta z. Okay, so that is y high times by z minus delta z times by delta x plus the strip on top. What's the strip on top? Well, it is x minus delta x wide. It is delta y deep, and it is z minus delta z into the page. So we've got x minus delta x times by z minus delta z times by delta y. So let's multiply those out. We've got x, y, delta z plus y, z, delta x minus y, delta z, delta x plus x, z, delta y, x, z, delta y minus x, delta z, delta y minus delta x, z, delta y plus delta x, delta z, delta y. Okay, so we can massively simplify that. We have two numbers, two small numbers, and we multiply them together, we get a really small number. So 0.1 times by 0.1 would be 0.01. If we get three small numbers and multiply them together, we get a really small number. So any of these terms where we've got two delta terms, such as this one here, that's approximately 0. That's approximately 0. That's approximately 0. And that is really small because we've got three delta terms, so that is definitely approximately 0. So my change in volume is simply x, y, delta z plus y, z, delta x, terms disappeared, plus x, z, delta y. That's disappeared, that's disappeared, that's disappeared. So that's my change in volume. Okay, so let's go back to this. Okay, the volumetric strain equals the change in volume divided by the original volume. Well, that's equal to the change in volume divided by the original volume. The change in volume we've now just said is x, y, delta z plus y, z, delta x plus x, z, delta y, all divided by x, y, z. That's equal to x, y, delta z over x, y, z plus y, z, delta x over x, y, z plus x, z, delta y over x, y, z. Okay, so clearly x and y cancel with x and y there, so you've got delta z over z. Clearly y and z cancel with y and z there, so you've got delta x over x. And clearly x and z cancel with x and z there, so you've got delta y over y. So that is equal to delta z over z plus delta x over x plus delta y over y. Okay, now that's our volumetric strain. Okay, so hence my statement earlier of our volumetric strain is simply the sum of three mutually perpendicular strains. So when we're talking about Cartesian coordinates, the volumetric strain is simply the strain in x, strain in y, plus the strain in z. We add those three mutually perpendicular strains to get the volumetric strain. So our volumetric strain is simply the sum of three mutually perpendicular strains. So let's now have a look at the situation that we're actually considering. Let's have a look at our volumetric strain for our cylinder. Okay, now we've just said that is the sum of three perpendicular strains. However, when we're dealing with our cylinder, we consider our cylinder, those three mutually perpendicular strains are not x, y, and z. But in terms of the terminology that we're using today, we've got the strain in this direction, which is our longitudinal strain. We've got our strain in this direction, which is our diametral strain. And we've got the strain in this direction, which is also our diametral strain. Okay, so our sum of our three mutually perpendicular strains is simply the strain in the longitudinal direction plus two lots of the strain in the diametral direction. And we've already shown today that actually the diametral strain is the same as the hoop strain. So that is the longitudinal strain plus two lots of the hoop strain. And our longitudinal strain is made up of two components, the strain caused by the longitudinal stress plus the strain caused by the hoop stress. So we plug that in, 1 over E, lots of the longitudinal stress minus Poisson's ratio times by the hoop stress. So that's our longitudinal strain. And we add on to that two lots of 1 over E, lots of hoop stress minus Poisson's ratio times by our longitudinal stress. We multiply those out, simplify them. What do we end up with? End up with 1 over E, lots of our longitudinal stress plus two lots of our hoop stress minus Poisson's ratio of our hoop stress plus two lots of our longitudinal stress. Our longitudinal stress, we've already said, is PD over 40. So that's 1 over E PD over 40 plus 2 lots of our hoop stress PD over 2T minus Poisson's ratio of our hoop stress PD over 2T plus 2 lots of our longitudinal stress PD over 4T. Okay, if we then factorize that lot, we end up with PD over 4T E lots of 5 minus 4 lots of Poisson's ratio is our volumetric strain. So therefore our change in volume is simply going to be our volumetric strain times the original volume. So that's PD over 4T E lots of 5 minus 4 lots of Poisson's ratio times by the original volume. Okay, so what have we done there today? Well, if we consider our cylinder, which is pressurized due to the fact we've got pressure inside it, we've introduced this idea of hoop stresses and longitudinal stresses. We've worked out how we can calculate those, what those are, and we've shown that our hoop stresses are twice as big as our longitudinal stresses. We've also, once we've done that, we've been able to work out our strains and therefore our change in lengths and our change in diameters. We've then gone on and shown that actually our diametral strain is the same as our hoop strain, and by considering that, that enables us to work out the change in volume due to the fact that we've pressurized this cylinder. Okay, next time we'll be having a look at the special case of a sphere, and we'll be having a look at effects of end plates, joint efficiencies, and so on. In the meantime, what I want you to do is have a go at there's some examples at the end of this handout. I'll upload this handout for you. Have a go at examples number 1 and number 2, and we can discuss those in class. Example number 3, you're not going to be able to do until you see the next video. Okay, so we'll go through those examples in class. We'll discuss any questions that you've got in class, and yeah, we'll take it from there. Okay, thank you. Goodbye.